Hello folks, there's kind of an approach to using the kinematic equations, and this is an example problem that's meant to sort of animate that approach. So you're in a hotel staring out this 1.5 meter tall window, and this ball comes screaming past. You see it for 2/10 of a second, then it's gone, then 12 seconds later it comes back. Assuming it bounced elastically at the ground, assuming it started from rest at the top of the building, how tall is the building? This is a problem you can actually take apart using kinematics, which is the reason why we're looking at it. And so I'm going to go through the steps that you would normally use to try to do this. The first step is you need to draw a sketch, and you need to put all the information that you know onto the sketch so that you don't have to try to keep it all in your head. So I'm going to make a drawing of my building. And so here's the top of my building, and it goes down to the window, and then it goes all the way down to the ground. Now I need a coordinate axis and an origin. So I'm going to go ahead and put a coordinate axis like so. I'm going to identify y equal to 0 to be at ground level. Having done all that, it's now time to start to identify points of interest. My first point of interest will be at the bottom of the window. I'm going to call its coordinate y1. I'm going to assume its velocity at that point is v1. Moving on to the top of the window, I'm going to probably call that y2, except I actually know this distance between here and here is 1.5 meters, so I'd probably incorporate that into the characterization of that point, or that coordinate. I'd also probably assign a velocity, an unknown velocity to that point right there. So here you can see I've done all of those things. I also know that the amount of time it took for the ball to go from there to there was 0.2 seconds. So here all that information has been placed. Here at the top, I know that the ball started from rest, so I know its velocity at this point. I would assume that the clock started at t equal to 0 when the ball started to fall, and I would probably identify this coordinate as just y at the top. So here you see all of that information. I know that it took 12 seconds for the ball to go from the bottom of the sill all the way down, bounce elastically, come all the way back up to the bottom of the sill again, which means that it took 6 seconds to go from there to there, so I need to include that. And lastly, something that it wasn't actually stated in the problem, but it's something that I know is true, and that is that the acceleration in the system as the ball accelerates downward was the acceleration of gravity, which is symbolically characterized as minus g, where g is 9.8 meters per second per second. And so I should put that bit of information in. So here's our acceleration term. I will be using the algebraic version in the equations, and then we'll put the numbers in later. So here are your kinematic equations, as I assume that you have them written down in your notes. And I'm assuming that you will probably memorize these for the test. There's actually something a little bit spooky about these as they stand. We need to talk about this, so we're going to take a little side trip, then we'll come back to the problem. So think back to the way we derived the kinematic equations. The first one that we derived, we started with a velocity versus time graph for a constant acceleration situation. So it was a nice linear velocity versus time graph. And we know that the slope of the velocity versus time graph is going to end up giving us the acceleration. So we determined what the slope was, the rise over the run, and we did this operation. And delta v over delta t is really saying the velocity at the end of the time interval. Here's the time interval. Here's the velocity at the end of the time interval. And you subtract that from the velocity at the beginning of the time interval, and that's how we figured out what delta v was. And as far as the variables that we were using in the context of the little problem here, this v at the end of the time interval was the same as v2. So we came up with this expression that said a equals v2 minus v1 over t. We brought the delta t up, we brought the v1 over, and we ended up with this expression right here. And so this is probably what you have in your notes. This is probably what you will memorize for the test. So far, so good. So let's go back to our problem, and let's take a look at the time interval during which the ball is passing by the window. If we were going to go ahead and use this relationship, which you have memorized, and we were to use it in the context of this section right here, this time interval right here, this is what you would write. Now when you look at this, this just doesn't look right. But if you think about what these variables actually mean, this is the generic kinematic relationship. And each one of these variables means something. It's telling you to get some bit of information and plug it into that slot right here. And what this bit of information right here is saying, go to the end of the interval, the time interval that you're looking at, and look to see what you've defined the velocity to be at, and put it into that slot right there. So what is the final velocity as the ball is passing by the window? Well, as it's passing by the window, the velocity at the end of the time interval is v1. And that's what goes right there. This is saying, go and look at your problem and identify what the velocity was at the beginning of the time interval that you happen to be looking at. So, if you look at what's happening, given the way we've defined our velocities, what is the velocity at the beginning of the time interval? Well, it's v2. And so that's what would go into this slot. There are two morals here. The first is that if you take a generic relationship like this, you have to know what each of the variables is telling you, how they're defined. Because if you don't understand how they're defined, you're not going to be able to use the expression reasonably. And the second is that you need to understand that physics is a thinking discipline. This is not a memory-driven discipline. You're not going to be able to get away with just memorizing stuff and then just sort of mindlessly throwing stuff down on the paper. You're actually going to have to use your head and think your way through problems. And on that happy note, let's go back to our problem. And it seems as though the area that we know the most about is the area around the window, so let's see what we can do with that. So what kinematic equation do we have that has time, acceleration, and coordinates associated with it? Well, if you look into your notes, you will find that this relationship right here works just nicely. You know t, you know a, you know what delta y is when you bring the y2 and y1 over. Delta y is minus 1.5. The only thing you don't know is what the initial velocity of the interval is going to be, which according to our sketch is going to be v2. So if you put all that information in down here and you solve for v2, you come up with minus 6.52. So I'm going to go ahead and take that velocity, I'm going to put it on my sketch, and then I'm going to think a little bit about what I'm trying to actually figure out. I'm trying to figure out this distance. At some point in time I'm going to have to figure out this distance. If I look at the sketch though, I can see that the one area I haven't dealt with yet that I know now quite a bit about is this area right here. I know the velocity at the top, I know the velocity at the top of the window. Trying to figure out this bit of information. I know what the acceleration is through that section. I don't know the time interval, but there happens to be a kinematic equation that doesn't include time, but does include all the other variables. If we go ahead and solve for what that change in position is, given that we know the acceleration and the two velocities, you will come up with an expression that looks like this. The change in position will be minus 2.17. Negative sign makes sense. You're ending up at a coordinate that is less than where you started, so when you take the difference between the two, the final is smaller than the initial. You'd expect this delta y to be negative. If you go ahead and, or when we go ahead and figure out what the total height of the building is, we'll simply have to take the absolute value. The last section we need to mess with is this section here. We probably are going to need to know what this velocity is, which we can figure out if we look at the window again. We know the time interval, we know the initial velocity, we're looking for the final velocity, and we know the acceleration. So we can use this relationship to solve. And if we do, we get the velocity v1 being minus 8.48 meters per second. We put that velocity in like so. So now we know the initial velocity, we know the time interval, we know the acceleration, and we're trying to figure out what the change in position is. This is the kinematic equation that has all of those variables associated with it. We put all the numbers in, come out with minus 227. So now we have all the deltas, and all we have to do is just add them all up, or at least their absolute values anyway, and we come up with the height of the building being 230.67 meters. So to use the kinematic equation sort of in summary, you want to start off by drawing a sketch. You want to define your coordinate axis along with x equal to 0 or y equal to 0 points. You want to identify points of interest and define parameters, coordinates, velocities, time intervals, etc. on that coordinate axis. You want to identify any hidden parameters. If you have the acceleration of gravity available to you, don't forget the fact that you know that information. And then you will simply want to use the kinematic equations to sort of pick away at the problem, determining parameters as you go and as needed in an attempt to try to solve the problem as stated. Anyway, that's pretty much it.